It's actually 8:31 over here, 11:31 over there. So
Yep.
I'd like to welcome everybody today. We have about 2, 4, 6, 8, 10, 12 people in the room. So welcome to our pre-symposium event, Programming Quantum Computers, Tools and Techniques for the Undergraduate Computer Science Faculty. Circumstances are as such. So out of the, many presenters, most of the presenters are online. We're going to start with a remote presentation from MIT. Professor William D. Oliver is going to present. I just want to say a few things. You can see on the projector. Professor Will Oliver is a principal investigator in the Engineering Quantum Systems group on the MIT campus and the Quantum Information and Integrated Nanosystems group at the MIT Lincoln Laboratory. He provides programmatic and technical leadership targeting the development of quantum and classical high-performance computing technologies. Professor Oliver's research interests include the materials growth, fabrication, design, and measurement of superconducting qubits, as well as the development of cryogenic packaging and control electronics involving cryogenic CMOS and single flux quantum digital logic. I'm going to switch to the screen where we have the connection with Boston.
Yep.
And the presentation is about Introduction to Quantum Computing. If you want to ask a question, that's the microphone. It needs to be turned on so that we can hear you. So with that, why don't we welcome Professor William Oliver.
Well, thank you very much. It's a pleasure to be here, and under these circumstances, I'm glad that we could still have the meeting and the conference. I'd like to talk to you about an introduction to quantum computing, and I'd also like to do it in the way that we often teach it, both to the professionals in the professional development classes we teach, but also to students here at MIT. And so, it won't be, it's what, 40 minutes, so it won't be the complete story, but I'd like to give a flavor of how this field is transitioning from what we might say is a scientific curiosity to a technical reality and an engineering discipline. But before I get started, let me show you a video first, and we'll start there, and then I'll pick it up once the video is completed.
We hear about quantum computers nearly every day in the news and in the popular press. That's what's exciting about quantum computing, and that's what it's said that quantum computers will solve certain types of problems, ones of tremendous importance to humankind, and problems that today are practically prohibitive or maybe even impossible to solve with current computers. We hear about pharmaceuticals and drug discovery, gaining a better understanding of new materials like high-temperature superconductors and how they work, new methods for machine learning, artificial intelligence, optimization problems, financial services and technology. Quantum computers will even challenge and change the way we securely communicate information. It certainly sounds like a fantastic and exciting future, which leads us to a few fundamental questions. What exactly is a quantum computer and what's it good for? More importantly, when will we have one?
Quantum computers are not just smaller, faster versions of classical computers. They're fundamentally different.
We're in the digital computer world, a bit, which is one basic element of information is a 0 or a 1, nothing else.
In a quantum computer, you can have a quantum bit or qubit that's in a superposition of 0 and 1.
We can design it, we can actually control it. We're actually engineering and manipulating quantum mechanics.
So when we'll have a quantum computer is a very interesting and nuanced question, and the answer will therefore be kind of finicky.
We've been saying quantum computers are 10 years away. We've been saying that for decades.
Depending on your definition, we already have quantum computers. They're just small.
Within my lifetime, I believe, and I won't say how old I am.
This is not decades away or 100 years away. That quantum age has now come.
Quantum computers aren't simply faster, smaller versions of the conventional computers we have today, nor are they another incremental step in the evolution of Moore's law. Rather, quantum computers represent a new, fundamentally different computing paradigm, one that carries tremendous advantage for certain types of problems of importance.
Quantum computing could really transform industries where there are significant optimization problems. You've got a lot of discrete or binary decisions to make to figure out, do you do this first or that first? This is where we shine.
Another way to understand the difference between classical and quantum computer is if you look at quantum systems of quantum simulation.
The quantum processor is a suitable tool for modeling other quantum systems.
Biomolecule systems, tons of systems that we use, material systems, work based on those quantum mechanical properties.
You kind of need a quantum machine in order to simulate quantum effects. When we can manipulate individual molecules and understand what's going on in those molecules, how they bond, then we'll be able to have a really good handle on generating new things, novel materials that might be very useful.
Still, we're just at the very beginning of quantum computing development, assembling and testing the first prototype processors. It's a bit like being in the 1950s at the dawn of transistor-based computing. And just as integrated circuits led to an information processing revolution last century, driving economic growth and productivity, many people today believe that quantum computing will have a similar impact this century.
Quantum computing and quantum algorithms present fundamentally new programming and algorithm design paradigms. How do we fundamentally unlock new ideas in computing? We're still learning a lot about how to improve the individual components as well as connect them together.
That's part of the fun. That's where I'm there to see what can we do to enable that increased complexity and functionality of these qubits.
We're really here at the very beginning, and I just find that tremendously exciting.
So indeed, it is a very exciting time, but as we know, there's also a lot of hype in the field, and so disentangling that is part of what I'd like to do today. And I should mention that video we just saw is the first video out of 160 videos in a professional development course that we've developed here at MIT, and I'll talk a bit more about that later. But before we get into that, let me neck down from quantum information science and technology in general refers to an array of technologies: quantum sensing, quantum networks or quantum communications, and of course quantum computing. And in a nutshell, this quantum information science utilizes a quantum mechanical description of nature to sense or to communicate or process information in ways that basically are unobtainable by a classical description of nature. And so it's a wide-ranging technology, but I'm going to focus on quantum computing today. And before I get into that, I think it's worthwhile to go back and look at last century and the development of the classical electronic computers we have today. So we know the triode vacuum tube was invented in 1906, and it was used for transceivers, basically amplifiers, for decades. And it was 1946 when we first had a vacuum tube-based computer called ENIAC, which I'm sure we've all heard of. Now, around that time, the transistor was invented at Bell Labs, and within about 10 years, we had the first fully transistor-based computer called TIXO, or TX0, developed here in fact, at MIT and Lincoln Lab. Now, this was a transistor-based computer, but it didn't look anything like the computers we have today. It took those three-legged transistors and soldered a bunch of them together, used a magnetic core memory, very different than the integrated circuits we know of. Now, those were invented in 1958, 59. But again, it was a couple decades before we got into the 70s, and we started seeing the circuits that we would recognize today as integrated circuits. So the Intel 4004, the 8008, et cetera. And then another 2 decades to get to the Pentium Pro, where we had millions of transistors, and then another couple decades to get to the billions of transistors, GPUs, multi-core processors that we have today. So, if we look back at this timeline, it's well over 100 years of development from the first demonstrations of the fundamental logic elements to where we are today. Now, we can compare with that quantum computing, which is, far more nascent. Richard Feynman in 1981 suggested that, if you want to simulate a quantum system, you should use a quantum system to do it, because it's very hard. We know there are lots of degrees of freedom, and there's, if it gets large enough, it's too hard for a classical computer to keep track of all that. Theorists thought about it. 15 years later, 20 years later, we started to see the first algorithms, notably Shor's algorithm for cryptanalysis of RSA, the first error correcting codes for a quantum computer, quantum annealing, adiabatic quantum computing, Grover's search algorithm, etc. Those were theoretical ideas. It was yet another 20 years before we got to the point where we are today, where we have the first nascent quantum computers that you can access online with maybe 20 to 50 qubits. So the takeaway is that, look, this is happening. Quantum computing's real. It's transitioning from scientific curiosity to technical reality. But we know as engineers and scientists that advancing from discovery to useful machines takes time. It takes abstraction and it takes engineering. And I guess the other point to make is that you must be in the game to play. And maybe it's not a surprise that the United States has many of the companies that led the information processing revolution last century because we were in it so early on. Okay, so what is a quantum computer good for? Well, the most general quantum computer, of course, is a universal fault-tolerant quantum computer. This is a quantum computer that can run any algorithm, any quantum algorithm, as well as any classical algorithm. But in fact, it often performs no better on a classical algorithm than does a classical computer. But for a certain set of quantum algorithms, it vastly outperforms them. One example here is Shor's algorithm, which I just mentioned a moment ago, which basically does period finding or prime factorization very efficiently. Here's the processing time in hours of a petaopt scale classical computer trying to crack an RSA key of bit length shown on the horizontal axis. And what you can see is that this classical petaops computer will scale exponentially in terms of the amount of time it takes to crack this key, whereas a quantum computer only scales polynomially in the size of that key. And so that is substantial, right? That is a very important application. But if it were the only one, maybe we wouldn't be so interested in this. Of course, governments would, but that's not really commercializable. That's not the only application. There are others, including database searching, sampling solutions to linear equations, and more, simulation, as I'll talk about in a moment. Now, here, for these types of problems, the quantum speedup is known to exist over known classical algorithms, but of course, if we can build a quantum computer large enough to really take advantage of this speedup. Now, in the nearer term, I should say that's the farthest off, the blue sky vision. In the nearer term, what we envision is having digital and analog quantum simulators, which are basically ASIC-like, application-specific, designed for a task. One example is given here is the biological nitrogen fixation problem to produce ammonia. It's one example of a quantum chemistry problem, drug development, material science. These are the kinds of problems that we expect this ASIC-like quantum simulator to be able to solve, and it can do so, we hope, in the nearer term as opposed to decades away. Now here again, for these types of problems, quantum speedup can exist over known classical algorithms, but again, we need to build a quantum computer large enough to realize that speedup. Now the third type of quantum computer is called a quantum annealer, and that's quite different than these other two, which are called gate model quantum computers. And a quantum annealer basically is an optimizer, and it optimizes things like supply transport, satellite tasking, pattern recognition. Optimization, of course, as we know, is ubiquitous, and just about every field or every industry is trying to optimize something. And so studying quantum annealers is very, very important. Now, it's unknown if a quantum speedup exists over known classical algorithms for a quantum annealer. Hasn't been proven that it will, hasn't been proven that it won't. But because of the ubiquity of optimization, it's important that we understand what a quantum annealer can do. Now, at the end of the day, if it is just a classical computer, but it vastly outperforms existing classical computers, well, that's fine, right? I think that that's still quite a useful computer. And I should say that here at MIT and groups worldwide are studying all three types of quantum computers. So to realize this promise of quantum computing, we've got to be able to engineer quantum systems, computers, that are robust, reproducible, and extensible. Okay, so I'd like to tell you now a bit about what the fundamental logic elements are of a quantum computer and how we think about them. So basically, any two-level system can be a candidate as the logic element for a quantum computer. And we could think of it as the electron in a magnetic field. It has a spin up or a spin down. They'll generally be at different energies, separated here. And what we'll do is we'll associate one of these, let's say the spin up, with state 0, which we write it in this funny way. It's a ket notation. Or spin down, which we're going to associate with state 1. Now, we represent this state on a Bloch sphere. And you could think of this as the planet Earth, basically. The North Pole, we're going to associate with state 0. And the South Pole, we're going to associate with state 1. And at the North Pole or the South Pole, this is basically a classical state. A transistor would be at the North Pole or the South Pole. Or this electron spin can be at the North Pole or the South Pole and just be a classical bit. But if we then continue this analogy with the planet Earth, of course, this vector that you see here, this orange vector, which indicates the state, doesn't have to be just at the North or South Pole. It can point anywhere on the surface of the Earth. And when it's anywhere but the North or South Pole, it's in a quantum superposition state, which is a manifestly quantum mechanical state. It's a single state, but it carries aspects of both 0 and 1 simultaneously with a weighting, which we call a probability amplitude. And these amplitudes, and of course the phases that are drawn on this Bloch sphere, are complex numbers. Now, if the vector happens to be pointed at the equator, then we call this an equal superposition state because the 0 and 1 are weighted equally, but there's a phase between them, as you can see. So that's just one example that we'll see throughout. Now, if we want to compare the classical and quantum bits and understand what does that buy us, basically, we can think of 3 spins shown here. Let's imagine that these are classical spins at this point, just classical bits. And so this represents 8 classical states from 0, 0, 0 all the way down to 1, 1, 1, different configurations of the spins. And these are just classical at this point. Now, quantum mechanically, we can represent all of those classical states simultaneously in a single quantum state. That's the difference. And you can see this massive superposition state shown here with 8 complex numbers. We could rewrite it this way, which makes it closer to the binary notation perhaps we're familiar with. And just to mention again that this state is a single state, but it required 8 complex numbers to describe it fully, right? And then you can start to imagine the exponential growth in the state space that happens this way. And so we can change our state space representation like this. We'll put those coefficients C1 through C8 over there. And now we're going to look at the real power of a quantum computer, which is quantum parallelism and quantum interference. Okay. So first we'll start with quantum parallelism. We're going to look at this first atom, which has a spin up or down, and we're going to apply to it some laser pulse, which flips the spin. It'll take spin up and flip it to spin down, and it will take a spin down and flips it to spin up. Now, we represent that on the Bloch sphere like this. So there's a spin pointed towards the North Pole. This pulse will flip that down to the South Pole, or it'll take the South Pole and flip it up to the North Pole. That's how it works. And our state space is shown here. It's a massive superposition state with these weighting coefficients across all of these states. Now, basically what this does quantum mechanically is this pulse, it's one pulse on one spin, but it's going to affect all of these coefficients simultaneously, the 2 to the n coefficients. And here's how it works. So we have before and after the pulse. And when we apply the pulse, wherever we had a spin up, well, that's going to flip to down. And so those coefficients, C1 through C4 associated with up, they now move down there to the spin down. Now, similarly, if we had a spin down for the states which correspond to that, they come with coefficients C5 through C8. They're going to flip up and they move over here. And so what we see is that we've applied one pulse on one spin, but we've changed all 8 coefficients, right? Or probability amplitudes. And so this is an example of what's called quantum parallelism. Now, the next part of what makes a quantum computer powerful is called quantum interference. And here, what we're going to do is we're going to look at a pulse which is half the amplitude of the last one, which means it does a pi over 2 rotation. It rotates the state 90 degrees. So we're going to do before and after again. And now let me take these one at a time. We're going to say that a spin up rotates 90 degrees, which brings it down to the equator. And we're going to associate that direction with a plus sign. So spin up goes to a combination, equal superposition of up plus down. Now, I'm not worried about normalization here. For people who are familiar with this, you know, there would be a 1 over square root of 2 here, but we don't need to worry about that for this discussion. So let's take a look at this spin right here associated with coefficient C5. That is going to, after the pi over 2 pulse, split to up and down. And so that coefficient C5 is associated with both of these states now. For a spin down, this rotates in the same direction, but you see it's now pointed in the opposite location. And so that's going to be associated with a minus sign now. And so this spin goes to up and down, but the coefficient C6 comes in with a minus sign. So what that means is that, okay, if C5 had equaled C6, these two add, and that's called constructive interference. But in this case, where they're subtracted, in fact, that probability amplitude goes to 0, and there's no longer any weighting on this particular aspect. And this is called destructive quantum interference. And of course, this happens, of course, across the entire register simultaneously. So this is also an example of quantum parallelism. And so this is really what provides a quantum computer its power. It's both the quantum parallelism and the quantum interference that occurs because we're applying one pulse to one qubit or one atom at a time, but we're affecting the entire register simultaneously. So this is an example of the classical and quantum gates that we use to control a quantum computer. And I think we're familiar with the classical gates like NOT gate, AND gate, OR gate, etc. And we know that with a handful of these, we have a universal set of gates with which we can perform any Boolean logic. Okay, and it's not a unique set. There are many combinations which can be used, but it's usually a handful of them. Now, similarly, on a quantum computer, we have a list of gates. There are gates which apply to one qubit and do rotations on just one qubit. They're listed here. There are also gates which apply to 2 qubits. I'll show an example of it in a moment, but you know, what it is that the state of one of these qubits affects what happens to the other one. That's a 2-qubit gate. And by analogy, we have universal sets of quantum gates which take handfuls of these single and 2-qubit gates, again, not unique, but with them we can perform any quantum logic, which basically means we can reach any point in the state space of the quantum computer with just these few handful of quantum gates. So let's look at an example of one. Here's a single qubit operation that's analogous to the classical NOT gate, which we know takes 0 to 1 and 1 to 0. The quantum NOT gate example or analog is called the X gate. Now the X gate also takes 0 to 1, and I'm showing an example of it here. You see that the state starts at the North Pole, and with this amplitude of the envelope of the field that we apply to do the rotation, it rotates at 180 degrees. And as you see, this is just going North Pole to South Pole. So basically at this point, it's just a classical gate. It takes 0 to 1. Where it gets interesting is when the qubit is in a superposition state. And what this field does is it still rotates the block vector 90 degrees around a particular axis, in this case, the x-axis, which is why it's called an X gate. But what you see is it starts and ends in a superposition state. And basically what we're doing is we're swapping the weighting function or the weights alpha and beta on this state. So that's a single qubit gate analog to NOT gate. Now there's a 2-qubit gate called control NOT, and we also have a nice analog for that. It's like the classical exclusive OR gate, which has inputs, as you know, X and Y, and outputs the exclusive OR X plus Y. And the truth table is shown here. And the analog to that is the quantum NOT gate, where you can see the truth tables look the same, basically just now written in this quantum mechanical notation. And we now have a qubit X and a qubit Y. And let me just describe briefly how this works. You know, the rotation of qubit Y depends on the state of qubit X. So let's have an input and an output, and we're going to assume that our input is in this state here, where qubit X is in a superposition state, 0 and 1, and Y is in the ground state. The target is in the ground state, the control is in the superposition state. So we can take these one at a time, that the 0, 0 state doesn't change, because if the control is in 0, you can check from the truth table that nothing changes. So we just end up with 0, 0. Plus, okay, when the control is in the 1 state, we're going to flip this target bit. It becomes a 1. And now what we see is we have something that's very special. It's called an entangled state, because this cannot be factored into an X component crossed a Y component. So this is a manifestly quantum mechanical entangled state derived from this quantum CNOT gate. So again, with a handful of these types of single and 2 qubit gates, we can do universal quantum logic. And what an algorithm would look like is the following. You start with a state of your computer, which is basically a complete superposition state, equal superposition state. All weightings in front here are equal. We feed that into the computer, and then, you know, according to some prescription, there's going to be combinations of single qubit gates like this, where it's 1 pulse that flips the entire register, followed by quantum interference, which we just saw, and that changes the values of the coefficients in front. We have 2 qubit gates like we just saw, where the state of 1 qubit does a rotation on the other qubit, followed by quantum interference, and this goes on and on according to the algorithmic prescription, with a goal that at the end of the day, almost all of the weighting sits in front of one of these aspects or states, which is the answer to the question that we posed or that the algorithm's trying to solve. Now that's very important, because when we make measurements, we know that measurement of a quantum system must yield just 1 output, right? And it does so with a probability that goes as the magnitude squared of these coefficients. And so if one of these is 1 or close to 1, with very high probability, we're going to get the right answer. And if we run the computer a couple times, we can convince ourselves that, yeah, indeed, that is the right answer. So there are a number of quantum algorithms and speed up associated with them, and I won't read through the entire table, but let me say that you know, the major algorithms, as I've described, simulation, such as quantum chemistry, factoring or related number theoretic algorithms, solutions to linear systems of equations, optimization, and search. You can see here the classical time it takes, you know, oftentimes exponential, and the quantum improvement or the quantum time, often polynomial or quadratic improvement. And so there's a substantial speed up for these types of algorithms. But again, if we can build a quantum computer big enough, we only see this advantage when we get to large sizes. And of course, there's still research going on to address some of these limitations shown here. So why don't we have a quantum computer today? Well, it's because these qubits are faulty. And there are 2 times that we care about. One is the coherence time, or the lifetime of the qubit, and the other is the gate time, how long it takes to perform an operation. So let's start with the coherence time. This is how long a qubit remains quantum mechanical. So we put our computer into some quantum state, and we know that state exactly at time t equals 0. But as soon as we get started, it starts to interact with its environment, basically uncontrolled degrees of freedom that we don't know about, or maybe we know about them, but we don't have control over them. And so over time, that state starts to blur and decay, and eventually it's completely lost. Now, the qubits are still there. It's just that the time evolution and where the qubit would end up at this time is completely unknown to us because of the interaction with the environment. And this time scale over which this happens is called the coherence time. Now, the gate time, as you might imagine, is the time required to perform one of these gate operations. And of course, the figure of merit then, intuitively, is how many gates can I apply within the coherence time that I have? And that's roughly 1-to-1 in what we call gate fidelity, which I'll talk about next. Now, it's important to note, I think, that long coherence times are good, but that's not in and of itself sufficient. And you can come up with a absurd example, for example, like a neutrino. Neutrinos are very hard to detect. They don't interact with their environment. They basically have infinite lifetime. That's good. But because they don't interact with their environment, we can't control them either. And so that gate time would become basically infinitely long, right? So it's both the lifetime should be long, but the gate time should be short compared to that. Okay. So with that, let's take a look at a few different qubit modalities, candidates for qubits. Now on this axis is this number of operations I can perform within the lifetime of the qubit, number of operations before an error. On this axis is the gate fidelity that it corresponds to. So if I have one error in 100 gates, that's 99%, 1 in 1,000, 99.9%, etc. On the horizontal axis is gate speed, and faster is better. Now, this dashed line that just appeared, this is the minimum level or threshold, and we want to be above that threshold in terms of performance for quantum error correction. So just as with classical error correction, we can build in resilience to the system by adding redundancy. But that adding redundancy only is a net win if the individual components are at least good enough. And that's indicated by this threshold. And of course, the going in the wrong direction. Yep, best performance is in the upper right corner. So there are a number of modalities which have shown single qubit gates, and they're working on 2 qubit gates. And these are spins, either nuclear spins or electron spins in silicon, or in an MOS, metal oxide semiconductor dot. And there are a number of other technologies which have demonstrated both single and 2 qubit gates. So basically a universal set of gates. And those include the ones that are shown here with the ovals, such as trapped ions, superconductors, silicon quantum dots, NV centers, nitrogen vacancy centers, and neutral atoms. The 2 leading candidates today are trapped ions, and here's some of my colleagues here at MIT and Lincoln Lab who work on it, and superconducting qubits, which is my own field of research along with my colleagues. And if I had to say in a nutshell what we're researching today, trapped ions are trying to make their gates faster, and they're also trying to improve this 2 qubit gate fidelity. Superconducting qubits are already pretty fast, and so we're just trying to improve our fidelity. In both cases, though, we're basically at or above this threshold line. So we're in the regime where we can start to think about quantum error correction. Now, even though there's an exponential speed up in principle, attainable, faster is better. You know, you still want to be faster. And, you know, you can think of an example where someday we have a quantum computer that can perform a task, and let's say it takes a day to perform that task. And that's exponentially faster. A classical computer would take, say, 10,000 years. Okay, fantastic. Now, this trapped ion system, all else being equal, if it runs 1,000 times slower, it now takes 1,000 days to get that answer. Now, that's still much less than 10,000 years, so it's certainly a quantum speed up, but on a human time scale, it's not so useful, right? And so we still have this classical notion that having faster quantum computers is better. Okay, now just to round this out, neutral atoms are also in this game. Here's some researchers from MIT and Harvard working on that, and also NV centers with folks working on it. So the takeaway is, look, there are many technology candidates for the development of a quantum computer. Which one is going to win? I don't know. And also, you know, very likely different technologies will emerge over time. Just like with a classical computer, we had the vacuum tube to begin with. We moved to bipolar junction transistors, later, you know, ECL, now, you know, complementary logic, CMOS, et cetera. So it very likely will emerge. And so there won't be just one winner. If we look today at the processors we do have, these are them. So we have the processor from Google, Rigetti, Intel, at least the backside. We don't actually see the processor here. IBM and the online quantum computers that they have, as well as the D-Wave system, which is a quantum annealer, and that's also online. But again, I want to emphasize we're at the first mile of a marathon, right? And to realize the promise of quantum computing, we have to make much larger systems. We have to engineer quantum systems. They got to be robust. They have to be reproducible. They have to be extensible. So with that, I just want to take a few minutes and talk about engineering these quantum systems. So my own research is in superconducting qubits. You might wonder, how do you build a superconducting qubit? Well, if you're an electrical engineer, you've recognized this circuit, an LC circuit, which is basically an oscillator or a resonator. And in fact, if you cool it down to very low temperatures, where the energy scale KT is much less than this energy scale h bar omega, where omega is the resonance frequency of the circuit, you in fact have a quantum system. It has discrete energy levels, which we can label 0, 1, 2, but it doesn't yet make a qubit because each of these energy levels are separated by the same energy or frequency, right? The resonance frequency. And that's because this is a harmonic oscillator. It has a harmonic potential profile. And in order to make it anharmonic, we need to add a nonlinear element. And so we could pick either the inductor or the capacitor. We pick the inductor because there's something called a Josephson junction, which has many properties, but one of which is that it's a highly nonlinear inductor. And so by putting a superconducting Josephson junction in parallel with a linear capacitor, we change the potential profile. And when we change it, these energy levels also change in their transitions. And what we see is the 0-1 transition has a unique frequency from the 1-2 and the 2-3, et cetera. And so we can draw a box around 0 and 1 and say that is our qubit. And that's how it works. That's how we design qubits. Now, this is the simplest type of qubit. Some have more junctions or more capacitors. We might add more sophistication to elicit some particular property, but at its fundamental level, this is a superconducting qubit. Now, we control these using straightforward microwave control and engineering. So what we see on the right here is a local oscillator which produces a microwave signal resonant with this resonator. And we do what's called IQ mixing, where we take a baseband pulse and we multiply it with this signal to create an enveloped output. And if we use the I channel, we call that in phase. There's no frequency shift of this tone. But if we use the Q port, then there's a 90-degree phase shift. Okay, and those will associate with the X and Y axis with what I'm showing you here. So we've seen this block sphere before, and we've seen this block vector rotating between the North and South Pole. But now this red arrow that's coming in and out is the envelope of this pulse right here. And whether it's rotating this block vector around the X axis or the Y axis depends on whether we're using the I or Q port of this mixer. Okay, so now what we see is we have let's start here. So now we're going to use the Q port. We do a pi/2 pulse around the y-axis. With half the amplitude, we'll only bring it up to the equator. That's a pi/2 pulse. And with another one, we'll go back to the North Pole, etc. So with just this standard microwave engineering, we're able to control superconducting qubits. Now, of course, if we want to build a system, we need to build an architecture. We need to start with an architecture. And here's one according to Cody Jones, which starts with the hardware at the bottom of the stack and the application at the top of the stack. And you see things that are familiar to computer scientists and electrical engineers. You know, there's a logical controller here, which needs to do the compiling and turn that application into the control that's going to be implemented on the physical qubits. But what's unique to quantum computers is this layer 2 and 3. And basically, because the qubits are faulty, every clock cycle, we need to try to protect the qubits, prevent them from having errors. And then when errors do occur, we need to detect those errors and we need to fix them. And the way that this happens, I'm going to show you in a moment. I like to use the analogy of lacrosse. And so I'll show 3 short videos which give the idea of what's happening in these first 3 layers. So at layer 1, we just have physical qubits, and they're faulty because they interact with their environment. And that's analogous, I would say, to this lacrosse player here, who's, if you're familiar with lacrosse, you want to keep the ball in the stick and then score at the goal. But this young person wasn't very happy with me because I told him to do lacrosse the wrong way, which is basically carry the stick, but don't do anything else. And so you see, as he's running, his environment is making his body jump up and down and makes his stick go up and down, and the ball just quickly falls out, right? And that's basically a qubit interacting with its environment. It's very faulty. So of course you don't do that. What you do is something called passive error suppression or dynamical decoupling. What you do is you cradle the stick, you swing it back and forth. Now it's open loop feedback. You don't think about it, you're not responding to anything, you just always do it, right? But what that does is decouples the ball from the noise of the player running, as you see here. So you see that he's cradling back and forth, and by doing that, the ball is decoupled from the running and the noise due to the running, right? And so cradling allows the player to keep the ball in his basket until he's ready to score a goal, as he does here. Okay. So that works very well. That protects qubits against many types of noise, in particular dephasing. But that's not the only kind of error that occurs. Sometimes energy relaxation occurs, and that occurs to the big D or the decoherence, the defense here, who's going to come up behind and just knocks the qubit out of whatever state it's in. And when that happens, okay, what do you have to do? Active feedback and error correction. So what you do is you first have to identify that you lost the ball. You then have to go over and pick it back up again, and then you start cradling, okay? That's basically what every clock cycle of a quantum computer algorithm looks like. You do these tasks, passive error suppression, active error suppression, and in parallel, of course, run the algorithm. So with that, let me come to the end of the talk. What's the lay of the land today? Well, if we look worldwide, there's substantial investment going on, and there has been for a couple decades around the world: Canada, US, Europe, Japan, China, Australia, Singapore, as well as other places. I didn't capture everything. But what's really amazing is in the last 5 years, the number of companies that have gotten involved has really exploded. And the reason is because they see, maybe not today, but in the future, there's going to be impact on their bottom line. And so it's in this context that, well, we've recognized that there's a new discipline developing called quantum engineering. But we also know that we need to continue the fundamental research in quantum science and engineering to be successful, because we don't have all the answers today. And so it's in this environment that we've created the Center for Quantum Engineering, which is an MIT initiative between Lincoln Laboratory and the Research Laboratory for Electronics on campus. So let me just highlight that. You can see our website here. The mission statement is straightforward. We want to establish this center dedicated to the academic pursuit and practice of quantum engineering to accelerate practical application. So of course, step one is defining what is quantum engineering and how are we going to educate tomorrow's quantum engineers. So is quantum engineering a new degree? Or is it a sub-discipline within electrical engineering or physics or some combination, right? Is it a, what that is, we don't know. And we have to develop the curriculum or the curricula, and we also have to write the textbooks, right, that surround that. Now, this should be done in concert with industry, and so we have a consortium model that does that. And of course, the goal is to maintain our expertise and our lead in quantum information. We have a large number of participants, both from Lincoln Lab and campus in this center. This is only a partial list of folks that are participating. And we also have a number of partnerships that target quantum computing. So one of them is a 3-year graduate fellowship sponsored by the NSA and the Laboratory for Physical Sciences. They also sponsor research and the development of this quantum curriculum that I just mentioned. We also have the industrial group, and an important part of that is they help us understand what's important to them so that they can recruit students. We teach the students the right thing, they recruit them. And then of course, one of the first things we did a couple of years ago, which is where that initial video came from, was we developed a 4-course series of professional development courses targeting people in industry already, people who need to pivot from whatever they learned to quantum computing. It was sponsored by IBM, and there are 2 basic tracks. One is the fundamentals of quantum computing, courses 1 and 2, and then the practical realities, courses 3 and 4. If you'd like to learn more about that, here's a website link here that'll take you to the right place. Oh yeah, so I guess I threw in this extra slide. Here is that link just again, just to show you that the professional development course started, I guess, almost 2 years ago now. We've had more than 2,000 learners in the intervening period. We're running it more often now. We also have several MOOCs, which are, basically videotaping our graduate student class on quantum computing. Okay. So last slide, what is quantum engineering? That's a great question. We're still figuring it out. But as I look at it, I think about the quantum test beds that we want to build for, to prototype future quantum systems. And I realize it incorporates just about every department that we have here at MIT, whether it's mathematics and physics or computer science, maybe chemistry because of the quantum chemistry problem, material science, both for developing new materials, but also the fabrication of materials that go into making high coherence devices, analog and digital circuits, the design, either the control electronics or the design of the chip itself, et cetera, control. And so it's really bridging what we might consider traditionally science and mathematics with classical conventional engineering disciplines. And these all have to come together to form this new discipline called quantum engineering. And again, whether it's its own new department or a new discipline or subdiscipline, I think that still has to be worked out. So with that, I come to the end. Main messages, look, quantum computing is happening, but it's a marathon. It's gonna take a while, but it is happening. It is real. Quantum engineering is an emerging discipline. We need to define its foundations. We need to educate and train quantum engineers, both at the university level, as well as those already in industry and professionals. Our course has commenced. Now, I wanted to mention that we are offering discounts to people at this meeting or your colleagues and friends. You can go to this website shown here to get a link to those discounts. I think it's 20%. Or feel free to contact me about any of what we've talked about today. Here's my email address. With that, I'd like to thank you for your attention.
So now anybody can ask questions. If you want to ask a question from the audience, you have to use that microphone and make sure that you turn it on before you ask the question. Or if any one of the other presenters want to ask a question, they can just go through Zoom.
Stunned silence. I guess that was either really good or really bad.
It was very clear.
Well, you know, I really appreciate the opportunity to speak with you today about what we're trying to do here. And like I said, I'd be happy to engage with people who are, you know, similarly interested in this topic. And, you know, I'd welcome, you know, your feedback about this or comments at any time. And again, thank you very much for your attention.
Okay, thank you so much. In the break, I'm going to show you briefly the two courses and how you can just get in and get a discount. We're going to have a short break for about 5 minutes, and then we're going to have a group of 2 presenters from Indiana University, and I'm going to introduce them in a few minutes. Thank you. Thank you.
Yep.
Okay, so if you were to go to, let's say, program, and this was the first presentation. If you scroll down, you have a link to an older presentation, and then these are the 2 links for 3 links. One is for the entire program, and this is for course 1 and course 2. So if you were to click here, it will take you straight to the program. There are 2 courses, and you get a discount on account that you are part of SIGCSE. All right, so if you wanted to purchase them both, you see the discount on that side. If, on the other hand, you don't want to take both at the same time, I mean, the discount applies to both, you can just go to the first one, Introduction to Fundamentals, and you know, it already puts in the discount, and you can submit.